So this tutorial deals with MCQ questions on physical quantities. I would highly recommend that you first try tutorial 1 before tackling this tutorial, because then you'll find this one a lot easier. The first two questions in this tutorial deals with the definition of a physical quantity. So before we try and answer these two questions, let's revisit the definition. It says a physical quantity is a measurable quantity that has a numerical magnitude or number and a unit. In question 1, it says, what is essential when recording a measurement of a physical quantity? So we need to look at which definition says that, or which statement here says that a physical quantity is a quantity that has a numerical magnitude or number and a unit. And clearly the answer is B. The measurement has a unit and a number or numerical magnitude. Why isn't it A? In A it says the measurement has an SI unit. The definition of a physical quantity doesn't specify that the unit must be an SI unit. So it can't be A. In any case, in A, there's no mention of a number or numerical magnitude. Why isn't it C? It says the measurement has a unit given as a base unit. Once again, this definition of a physical quantity doesn't specify that the unit must be a base unit. And then secondly, there's no mention of a numerical magnitude or number here. Why isn't it D? It says the measurement is from an analog scale. But once again, this definition doesn't specify that the measurement must be from an analog or a digital scale, or even a digital scale. So clearly then, it can't be D. And also in D, there's no mention of a unit and a numerical magnitude or number. Then in question 2 it says, what is needed to accurately represent all physical quantities? The answer here is C, because if we recall, it says the definition of a physical quantity is that it's a measurable quantity that has a numerical magnitude or number and a unit. So in C it says a unit and numerical magnitude. Why isn't it A? The definition of a physical quantity doesn't specify that it must be a base unit. Why isn't it B? Once again, the definition doesn't specify that a number must be expressed in standard form. Then why isn't it D? The definition of a physical quantity doesn't specify that the unit must be a SI unit. So C is the correct answer here. Then in question 3 it says, which term represents a physical quantity? In A it says the meter. The meter is not a physical quantity, it's a unit of measurement. We use the meter to measure length width. Then once again, the coulomb is not a physical quantity, it's a unit of measurement. And we know that the coulomb is the unit of measurement for charge. So it's not A or B. In D we have the Newton, and we know that this is the unit of measurement for force. So the Newton is not a physical quantity, it's a unit of measurement. The answer here then is C. Pressure. We know that pressure equals force divided by area. And pressure is an example of a physical quantity. In order to be able to answer the next few questions, you need to memorize the contents of this table. This table gives the base quantities that you need to know for AS physics together with the SI units. So these are SI base units. The base quantities, of course, are length, time, mass, temperature, and current. And the SI base units are meters, seconds, kilograms, Kelvin, and amperes. So in number 4, it says, which quantity is not an SI base quantity? So we need to look at which of these quantities do not appear on the table, or which quantity does not appear on the table. And of course, the answer is charge. Mass, temperature, and time. So mass, temperature, and time do appear on this table as base quantities. Then in number 5, which unit is an SI base unit? Once again, we need to see which one of these appear on the table. And we can see that the ampere does appear on this table as an SI base unit. Of course, coulomb, degrees Celsius, and gram does not appear or do not appear on the table. Then in number 6, which unit is not an SI base unit? Once again, the coulomb does not appear on the table as an SI base unit. So here the answer is C. Let's look at question 7. It says, which definition is correct and uses only quantities rather than units? Let's look at A. It says density is mass per cubic meter. We know this definition is correct because density is mass per unit volume, and volume is measured in cubic meters. So the definition here is correct. However, cubic meters will be units and not a quantity. So the cubic meter is a unit and not a quantity. So even though mass is a quantity, the cubic meter is a unit. And we need to express the definition in terms of quantities only. So the answer is not A. Then in B, we have potential difference is energy per unit current. Here, both energy and current are quantities. However, the definition of potential difference is energy or work done per unit charge and not per unit current. So here the definition is incorrect. Then in C, pressure is force per unit area. We know this definition is correct. And both force and area are quantities. They are not units. So the answer is C. Why is D incorrect? It says speed is distance traveled per second. This definition is correct. Distance is a quantity, but the second is a unit of measurement. And hence D is not the answer. In number 8, it says which pair of units contains one derived unit and one SI base units. In A, we have amperes and coulombs. We know that the ampere is an SI base unit because it does appear in this table that you need to memorize. The coulomb is a derived unit. It doesn't appear in this table as an SI base unit. So clearly the answer then is A. Why is it not B? Both kilograms and Kelvin appear in this table as SI base units. Both meters and seconds appear in this table as SI base units. So it's not B, neither is it C. Why is it not D? The Newton and the Pascal do not appear in this table as SI base units. So they are both derived units. Going to number 9, it says, what is the unit of weight in terms of SI base units? We can start with the equation for weight. The weight W is the mass times G, and G is the gravitational acceleration. Now, what are the SI base units? We know that mass is in kilograms and acceleration, gravitational acceleration, is in meters per second squared. So here the answer is B. In number 10 it says, which unit can be expressed in base units as kilogram meters squared per second squared? Let's look at A. We know that a joule is the derived unit for energy. So in order to answer this question, we need to express energy in terms of the SI base units. Now, we know that energy is work done. So the work done, or energy, is force times the displacement. We also know that F equals ma. So work done, or energy, will be MAS. The SI base unit, or SI unit, for mass is the kilogram. Acceleration is meters per second squared. And S is displacement, which is in meters. We can simplify this. M times M is M squared. So this will be the energy or the work done in terms of the SI base units. And we know then that this will be the equivalent of the joule. And this is in fact what we have here. So the answer is A. Then in number 11, it says which SI unit expressed in base units is not correct. Let's look at A, the unit of force. We know force is mass times acceleration. And we know the units of mass. The unit of mass will be kilogram. And acceleration is meters per second squared. So A is correct. Then B, the unit of momentum. We know momentum P is mass times velocity. And expressed in SI base units, M is in kilograms, or mass is in kilograms, and velocity is in meters per second. So B is also correct. Let's look at C. So C, pressure. We know that pressure, P, is force per unit area. And force, of course, is MA. Then what are the SI base units of pressure? Mass is in kilograms. Acceleration in meters per second squared. And of course, area is in meters squared. We can simplify this. Here we're dividing the m's, so we can subtract the powers. There's a power of 1 here that we don't write. So 1 minus 2 is negative 1. So it's m to the negative 1 per second squared. And of course here we have kilograms per meter squared per second squared, as opposed to kilograms per meter per second squared. So C is the wrong answer. Then in number 12, it says which expression using SI base units is equivalent to the volt. We know that the volt is the unit of measurement for potential difference, V. So we can start with the definition of potential difference. It's the amount of energy or work done per unit charge. Now, work done is force times displacement. And we know that charge equals current times time. We get this IT from the fact that current is defined as charge per unit time. And that means that when we make Q the subject here, we get Q equals IT. So that's where we get this from. Then, of course, force is mass times acceleration. Now we can bring in the SI units. We know for mass, it's the kilogram. Acceleration is meters per second squared. And displacement is meters. Current we know is amperes. So ampere seconds. We can simplify this. So m times m is m squared. Then we have s to the power of 1 in the denominator. We can subtract the powers. So s to the negative 2 divided by s to the 1. Negative 2 minus 1 is negative 3. So it's s to the negative 3. And we can bring the amperes to the top. It becomes a to the negative 1. So we can check which answer it is. And of course here we can see that it's not going to be a, because here we have seconds to the negative 1. And we need seconds to the negative 3. So our answer here will be D. In number 13 it says, which of the following could have the same units as force? And we're given these 4 options. Let's start by looking at the units of force. So the SI base units. We know force is mass times acceleration. And so the SI base units will be kilograms for mass and meters per second squared for acceleration. Let's consider the first option here. It says energy over distance. We know energy is the same as work done, so W, and distance we can call x. The work done is force times displacement. And now we can bring in, well, before we bring in the SI base units, we can write force, F, as MA. Now we can bring in the SI base units. Mass is in kilograms. Acceleration in meters per second squared. And S is displacement, which is in meters. All over distance, and distance we measure in meters as well. The m's here will cancel, and we're left with kilogram meter per second squared, which is the same. These are the same SI base units as those for force. So the answer here then is A. Then in number 14 it says, which two units are identical when expressed in terms of SI base units? In A, we have joules per coulomb and kilogram meter squared per second squared per ampere. In order to answer this question, we need to express the joules per coulomb in terms of SI base units. Now, we know that the joule is the SI unit for energy. And we know that energy is work done, which is force times displacement, which is MAS. And so the SI units, for work done, the SI base units will be kilograms meters per second squared times meters for displacement. And we can simplify this. So m times m is m squared. So this then will be the SI base units for energy. So this must be the equivalent of 1 joule. So this is a joule. I just want to create some more space here. Let's look at the SI base units for the coulomb. We know that charge is measured in coulombs. And we know that charge equals current times time. So the SI base units then for charge will be amperes for current and seconds for time. Now we know this is the equivalent of 1 coulomb. So we want C to the negative 1 So c to the negative 1 will be a to the negative 1 times s to the negative 1. Now, we need joules per coulomb. So joules per coulomb will be this kilogram meter squared per second squared. So joules per coulomb, which is the coulomb to the negative 1 is a to the negative 1, s to the negative 1. And we can simplify this. S to the negative 1 times s, or rather s to the negative 2 times s to the negative 1 is s to the negative 3. And of course, what we get here is not the same as this, because here we have s to the negative 2 and not s to the negative 3. So we know that the answer can't be A. So let's get some space here. So we want to consider B now. It says joules seconds. Now joules we know, so joules seconds. Joules we know is this as SI base units or in SI base units. And in times seconds, so times S, we can simplify. Then s to the negative 2 times s, there's a power of 1 here that we don't write. When we multiply the s's, we add the powers. So negative 2 plus 1 is negative 1. So it's s to the negative 1. And this is what we have here. So the answer here then will be B. In number 15 it says, when a beam of light is incident on a surface, it delivers energy to the surface. The intensity of the beam is defined as the energy delivered per unit area per unit time. What is the unit of intensity expressed in SI base units? So we start with the definition of intensity given here. The intensity I, we can call it I, is the energy. Now energy is the same as work done, so we can write W for work done. The energy delivered per unit area per unit time. Now we can rewrite the work done as force times the displacement. And of course, force equals MA. We can bring in the SI units. Mass is in kilograms. Acceleration in meters per second squared. So meters per second squared. And displacement S is in meters. All over the area, which is in meters squared, and the time, which is in seconds. We can simplify this. The numerator here, or in the numerator, m times m will be m squared. Then s to the negative 2 divided by s. We can subtract the powers. There's a 1 here which we don't write. So negative 2 minus 1 is negative 3. And this is all over m squared. These can cancel, and we're left with kilograms per second cubed. And of course then the answer here is going to be D. In number 16 it says, which combination of units could be used for expressing the power dissipated in a resistor? So we can start with the definition of power. It's energy over time or work done per unit time. So W over T. And work we know is force times the displacement. Now, what's important to note here is that N, in other words, the Newton, is part of all these answers. It's part of each of these answers. So we can bring in the SI units. We know force is in newtons. Of course, the Newton is a derived unit. Then the SI base unit for displacement S is the meter. And for time t, it's the second. We can manipulate this. We can bring the s to the top, and it becomes s to the -1. So then, of course, D will be the answer. In question 17, it says the force F between 2 point charges, Q1 and Q2, a distance r apart, is given by this equation. So F equals K Q1 Q2 over r squared, where K is a constant. What are the SI base units of K? So we want to make K the subject of the formula here, and we can start by multiplying both sides of this equation by r squared. So on the left-hand side here, we'll get FR squared. On the right-hand side of the equation, the r squareds cancel. So we're left with K, Q1, Q2. We want to isolate K, so we can divide the Q1, Q2 into the FR squared. So now we have K the subject of the formula. We know that F equals MA. Then we want to write the charge here, or the charges, in terms of current. We know that Q, the charge, equals the current times the time. So Q equals IT. Q1 here we can therefore replace with I1, T1, and Q2 with I2, T2. Now we can bring in the SI units, or SI base units. M is mass, so that's in kilograms. Acceleration in meters per second squared. R is a distance, so that's in meters, so it's r squared, so meters squared. The current here will be in amperes, and the time in seconds. So AS times AS. We can simplify this. I'm going to continue over here. M times M squared is M cubed. A times A is A squared. And S times S is S squared. When we divide the s's here, we can subtract the powers. So -2 minus 2 is -4. We can take the a squared to the top. It becomes a to the -2. Now we check which answer gives the same result as we have here. And of course it's B. In number 18 it says the mobility mu of electrons traveling through a metal conductor can be calculated using this equation. So mu equals E over m times tau. So this is the Greek symbol tau. So mu equals E over m times tau, where E is the charge on an electron and m is its mass. The average time between the collisions of an electron with the atoms in the metal is tau. So tau is the average time. What are the SI base units of mu? So we can start by rewriting the charge E here as IT. Remember that Q equals IT. So charge Q equals current times time, and E is just another symbol for charge Q. So this is over m times tau. Now we can bring in the SI base units. I, of course, is current, so that's in amperes. T is time, that's in seconds. M is mass, which is in kilograms. We said that tau is the average time between collisions. So that will also be in seconds. Then S times S is S squared. We can bring the kilograms to the top and it becomes kilograms to the -1. And of course, comparing this here with the answers given, the correct answer will be B. Let's look at question 19. The average kinetic energy E of a gas molecule is given by this equation. E equals 3/2 kT, where T is the absolute or Kelvin temperature. What are the SI base units of K? We want to make K the subject of the formula, but we can first get rid of this fraction by multiplying both sides by 2. So then on the left-hand side we have 2E. On the right-hand side the 2's will cancel and we're left with 3kT. We want to isolate K, so we can divide the 3t into the 2e. So then K is 2e over 3t. Now E is energy, and we know that energy is the same as work done, which is force times displacement. So E we can replace with force times displacement S. Now we can bring in the SI base units. Actually, before we do that, we can rewrite force as MA. And now we can bring in the units, or SI base units. We can ignore the 2 and the 3 because they are constants without any units. Then M is the mass, so that's kilograms. A is acceleration. And S is displacement, which is in meters. Of course, T is the absolute temperature, so that's in kelvins, or Kelvin rather. So then we have M times M is M squared. We can bring the K to the top and it becomes K to the -1. And we can see that the answer is D. In question 20, it says the luminosity L of a star is given by this equation. So L equals 4 pi r squared sigma times T to the 4. Where R is the radius of the star, T is the temperature of the star, and sigma is a constant with these units. So W m to the -2, K to the -4. Of course, W referred to the watt, so this is watts. We can go to the units straight away. So 4 and pi are constants without any units. Then r squared, r is the radius, and we know that it's a length measured in meters. So r squared will be meters squared. Then we have sigma, and we are told sigma has these units. Then we have temperature to the power 4, so that's Kelvin to the power 4. We can simplify this using the laws of exponents, and we can add, because we are multiplying the m's, we can add their powers. So 2 plus -2 is 0. M to the 0, of course, is 1, because there's this exponential law that anything to the power 0 is 1. So essentially, m squared here cancels with m to the -2. Then the same with the case, we can add the powers. -4 plus 4 is 0, and k to the 0 is 1. So essentially these two also cancel, and we are left with W, which is the watt. We need to express the watt in terms of the SI base units. And we know that we use the watt to measure power with. So the definition of power is work over time. So energy over time or work over time. And work is force times displacement. Force is MA. Now we can write down the SI units or SI base units. Mass is in kilograms. Acceleration is in meters per second squared. And of course, times displacement, which is in meters. Time is in seconds. I'm going to continue over here. We can simplify using the laws of exponents. So m times m is m squared. We can subtract the powers of the s's because we are dividing. So s to the negative 2 divided by s, there's a 1 here that we don't write. Negative 2 minus 1 is negative 3. So s to the negative 3. And comparing what we have here with these answers, we can see that the answer is C. Here it says, at temperatures close to 0 Kelvin, the specific heat capacity C of a particular solid is given by this equation. C equals B times T to the power 3. Where T is the thermodynamic temperature. Now, the thermodynamic temperature is the same as the absolute temperature, which is measured in Kelvin. And B is a constant characteristic of the solid. The SI unit of specific heat capacity is joules per kilogram per Kelvin. What is the unit of constant B expressed in SI base units? Since we want the SI base units of B, we can start by making B the subject of the formula in the equation. So B will equal C over T cubed. We can bring in the units of measurement. So the units then, we are given the SI units for specific heat capacity C. So that's joules per kilogram per Kelvin. This is divided by, or C is divided by T cubed. T, of course, is temperature, so it's Kelvin cubed. Now we can simplify this. Since we are dividing the case, we can subtract the powers, so negative 1 minus 3 is negative 4. Now, note that in these options, we do not have a J for joule. So we need to replace the joule here with its SI base units. And we know that we use the joule to measure energy with. So energy equals work done, which is force times displacement. F equals MA, so MAS. So the units of measurement then for energy or work done will be kilograms, mass in kilograms, acceleration in meters per second squared, times S, which is displacement, so times meters. We can simplify this. M times M is M squared. So we can replace the joule here with these units. So let's do that. So we're going to have kilograms, meters squared per second squared, replacing the J here. Then kilograms to the negative 1, K to the negative 4. We can simplify this. So we have kgs to the power of 1 here. We're multiplying the kgs so we can add the powers. 1 plus negative 1 is 0. So we're going to end up with kgs to the 0, which is 1. So essentially these will cancel. And we're left with meters squared per second squared per Kelvin to the 4. So K to the negative 4. We can compare what we have here with these options. And we see that the answer is B. In question 22, it says, the speed V of a liquid leaving a tube depends on the change in pressure, delta P, and the density rho of the liquid. The speed is given by this equation. So V equals K, then brackets delta P over rho, all to the power n, where K is a constant that has no units. What is the value of n? So we can start by writing both sides of this equation in terms of SI base units. On the left-hand side, we have speed, and we know it's in meters per second. Then K doesn't have any units, so we can ignore it. Then we have delta P, the change in pressure. So we want the SI base units of pressure. We know that pressure is force over area. Force, of course, is MA. And so pressure in terms of the SI base units are meters in mass in kilograms, acceleration in meters per second squared. Area is in meters squared, so over m squared. We can simplify this. We're dividing the m so we can subtract the powers. So m to the 1 divided by m squared, 1 minus 2 is negative 1. So it's m to the negative 1. And of course, s to the negative 2. So we can plug it into the right-hand side here in the place of delta P. All to the power n. Then it's all over density. So we want the SI base units for density. And we know density is defined as mass per unit volume. And of course the mass is in kilograms. Volume is in meters cubed, which when we take it to the top here becomes m to the negative 3. So density here we can replace with kgs times m to the negative 3. Let's get some more space here. We can simplify what's inside the brackets here. The kgs will cancel. Since we are dividing the m's, we can subtract the powers. So negative 1 minus negative 3 is negative 1 plus 3, which is 2. So we have m squared. Then the same with, well, we only have one s at the top here. So we can rewrite it. Now we're going to use a law of exponents on the right-hand side here. We know a to the m, all to the n, is a to the m times n. So when we have brackets, we multiply the powers. So this we can apply, this rule we can apply here. So 2 times n is 2n. Negative 2 times n is negative 2n. Now remember, we need to find the value of n. We have an equation here. On both sides we have an m and an s. Now the powers on the left hand side must equal the powers on the right hand side. For example, here on the left hand side we have m to the power 1. On the right hand side we have m to the power 2n. So that means that 2n must equal 1. And we can solve for n here, and n becomes, or n is equal to 1 over 2, or a half. So the answer here is going to be A. In question 23, it says the speed v of waves on a stretched wire is given by this equation. So v equals t to the power of p, mu to the power of q, where t is the tension in the wire and mu is the mass per unit length of the wire. What are the values of p and q? Let's start by finding the SI base units of t and mu. Now, we're told that T is the tension in the wire. Tension is a force, so T equals F, which equals MA. Then the units, SI base units, will therefore be kilograms for mass and meters per second squared for acceleration. We're told that mu is the mass per unit length. So m over L. And in the units, so the units for mu, mass in kilograms, and L is a length, or length, so the unit will be the meter. So when we bring the meter to the top, it becomes m to the negative 1. Now we can go back to the equation and plug in the SI base units on both sides. So V is in meters per second, and this must equal T to the P. And of course the tension is the same as force, so we'll have these units. So all to the P, then multiplied by mu to the Q. And mu has these units. We can simplify the right-hand side using the laws of exponents. And we're going to use this law of exponents, a to the m all to the n equals a to the m times n. So when we when we have brackets, we multiply the powers. So we're going to multiply all the powers inside these brackets with the powers outside. So this is kgs to the 1. So 1 times p is p. So we end up with kg to the p. M to the 1, we multiply the 1 here with a p and we get m to the p. Then negative 2 times p is negative 2p. So s to the negative 2p. Then this is times, this is kg to the 1. So 1 times q is q, so we get kg to the q. Then negative 1 times q here is negative q. So m to the negative q. We can simplify the right-hand side further. Kg to the p times kg to the q. We add the powers, so it's kg to the p plus q. Then we have m to the p times m to the negative q. Adding the powers, we get m to the p minus q. And then, of course, this is times s to the negative 2p. Now, in this equation, the powers on the left must equal the powers on the right. There's no kg on the left. So we know that the power of the kg must be 0. So p plus q must be 0. And that means that p is equal to negative q. Now we can compare the s's, the powers of the s's, for example. So the power here of negative 1 must equal the power of negative 2p. So negative 2p, the power of s on the right hand side, must equal negative 1, the power of s on the left hand side. And we can solve for p here, and we get p is a half. We already know that p is equal to negative q. Another way of putting this is q is equal to negative p. So if p is a half, q must equal negative a half. And so the answer here will be C. In question 24, it says, what is the equivalent of 2000 microvolts? Now, just to note that micro is the same as mu. So this is the same as 2000 mu volts. We want to change this to volts. And we know that micro or mu is 10 to the negative 6. So this is the same as 2000 times 10 to the negative 6 volts. We can use powers of 10 here for the 2000. It's 2 times 10 cubed. We can use the laws of exponents and add the powers of 10. So 3 plus negative 6 is negative 3. So 2000 microvolts or mu volts is the same as 2 times 10 to the negative 3 volts. And we know that 10 to the negative 3 is milli. So this is 2 millivolts. And the answer is B. Then in question 25 here, it says the diagram shows the reading on an analog ammeter. Which digital ammeter reading is the same as the reading on the analog ammeter? So on this meter. Let's start by getting the actual reading in milliamps on this analog ammeter. So the large divisions here, we have 1, 2, 3, 4, 5 large divisions. So we know that the reading will be 1 point something. Let's look at the smallest division. We want the value of the smallest division. So we have 1, 2, 3, 4, 5 small divisions from 0 to 1. So the value of 1 or the value of the smallest division will be 1 divided by 5. In other words, 0.2. This will be the value of the smallest division. So then to write down the reading here, we have 1, 2, 3 small divisions. So 3 times 0.2 is 0.6. So then the actual reading in milliamps on this analog ammeter will be 1.6 milliamps. Let's look at our answers here. C gives the reading in milliamps and it says 16.0 milliamps. Of course, we know that the reading is 1.6 milliamps. So we know that it can't be C. Let's consider D. In D, the reading is given in amperes. So let's convert milliamps to amperes. We know that 1.6 milliamp or milliamps will be 1.6 times 10 to the negative 3 amps. So we have to divide the 1.6 by 1,000. So it's 0.00. So let's see, 1, 2, 3. 0.0016 amps. Now, in the answers here, it says the reading in amperes is 1.60, which is clearly not the same as what we get here. So we know it also can't be D. Let's consider option A. In A, the reading is given as 1,600 mu amps. So let's convert this to amps and compare it to what we had here. So 1,600 mu amps is the same as 1,600 times 10 to the negative 6 amps. And so we need to divide 1,600 or 1,600 by 10 to the 6th. So basically by 1 with 6 zeros. Now, when we do this, we're going to get 160 amps. So clearly it's not A, the answer is B.